Good day, everyone. In this video, I will going to discuss the first part of the analytic trigonometry. Your takeaway or your takeaways for this lesson are as follows. First is you will be able to verify trigonometric identities, and the second one is you will be able to apply the different trigonometric identities to simplify trigonometric expressions. When we talk about identity, it is an equation that is satisfied by every number for which both sides are defined. These identities play an essential role in calculus, especially in simplifying expressions and determining whether expressions are equivalent. Now, for this part, you will be able to learn the different trigonometric identities in order to simplify trigonometric expressions. Now, in the simplification process, the first part is the uh, the understanding or the know-how of the different trigonometric identities. But the rest of the solution is more on the methods that you have learned in simplifying algebraic expressions. That it's why don't forget those methods that you have learned in the first part of our subject, that is all about simplifying algebraic expressions. Now, let's start with the first identity. These are the odd and even identities. So each of the six trigonometric functions is either odd or even. So recall that a function is said to be an odd if f of negative x is equal to the negative of f of x, and it is even if this expression will satisfy. So if you have f of negative x, if that is equal to the original function that is f of x, then we can say that the function is even. Now in the trigonometric uh, function, we will use the unit circle in order for us to track the positive and the negative angles. So in our unit circle, let's pick a point right here that is located in the fourth quadrant. So the coordinates are negative y and positive x, and this is our angle theta. This is negative, it's because the rotation of this angle is clockwise. Now in quadrant 4, the cosine and its reciprocal, which is the second, are the only positive identities. The rest are all negatives. That is why for our odd identities, we have a sine of negative of the angle is equal to the negative y over 1, or simply that's the negative of the sine of the positive angle. For the cosecant, so cosecant of negative angle is 1 over negative y, so we have your negative cosecant of theta. And for the tangent of the negative angle, we have the negative tangent of the angle. It's because in the numerator for tangent, we have here a negative y. That is why the final expression is negative. Now for the cotangent, so cotangent, as we all know, is the reciprocal of the tangent. So if the result of the tangent of the negative angle is negative, same goes with our cotangent. So cotangent of the negative of an angle is equal to the negative of the cotangent of the positive angle. For our even identities, we only have two, as what I have mentioned from this statement. So we have the cosine of the negative of the angle is equal to x over 1, or that is equal to the cosine of the positive of the angle. So even if we have a negative acute angle, the cosine is still equal to the original. That is if the angle is positive. Next, we will proceed to the reciprocal of the cosine, which is the second. So the second of the negative of an angle is simply equal to the second of the positive angle. So these are our odd and even identities in trigonometry. Now let's proceed to the cofunction identities. So if the angle is between 0 to 90 degrees, so that's from 0 to pi over 2, then the angle theta and pi over 2 minus theta are the measures of the acute angles of a right triangle as shown right here. So if this is our theta, the equivalent cofunction angle is simply pi over 2, which is 90, minus theta. Take note that the sum of the interior angles of a right triangle or any triangle is equal to 180. So if we're going to add the interior angles of this right triangle, it will uh, equal to pi. Now, the term cofunction comes from the fact that these angles are complementary. So the complementary angle for uh, theta is equal to 90 minus theta, or that's pi over 2 minus theta. Now, let's generate the cofunction identities, starting with the sign. So if we have the sign of 90 minus theta, if we're going to refer our analysis or our derivation in this right triangle, so that is equal to the ratio of the opposite of this angle, that is A, over the hypotenuse, which is C. Now, on the theta's perspective right here, so the ratio of A over C is simply equal to the cosine of theta, because A is adjacent to theta and C is our hypotenuse. That is why if we have a sine of the complementary angle of theta, that is also equal to the cosine of the given angle. Now, for the cosine, so if we have cosine of 90 minus theta, upon looking at the right triangle, the cosine of this angle is the ratio of the adjacent side, which is b over the hypotenuse. So we have here b over c. Now, the ratio b over c is also equal to the sine of theta, because the side b is now opposite to angle theta and c is our hypotenuse. So the cosine of the complementary angle of theta is simply equal to the sine of theta. Now for the tangent, so tangent of 90 minus theta, we all know that tangent is the ratio of the opposite side over the adjacent. So for this angle, the opposite side is A, and then the adjacent side is B. So in the theta's perspective, the ratio of A over B is simply equal to the cotangent, because cotangent is the reciprocal. So B here is the opposite, and A is the adjacent. So cotangent is adjacent over opposite. Next, for the cotangent, so cotangent of 90 minus theta, we all know that cotangent is the ratio of the adjacent, which is B, over the opposite. And in terms of theta, B over A is simply equal to the tangent of theta, because tangent of theta is opposite over the adjacent. Now, for the secant of 90 minus theta, or pi over 2 minus theta, so secant is the reciprocal of cosine. That is the hypotenuse over the adjacent. So that's C over B. And in terms of the angle theta, C over B, so C is the hypotenuse, B now is the opposite side of our theta. So we will use the reciprocal of the secant, and I mean the sine, and that is the cosecant of theta. And lastly, for the cosine of this complementary angle, that is pi over 2 minus theta. So cosecant is equal to the ratio of the hypotenuse over the opposite side, so that's C over A. And in terms of the angle theta, C over A is equal to the hypotenuse over the adjacent. And the ratio of the hypotenuse over the adjacent will give us the secant of theta. So these are our cofunction identities. Now let's proceed to the Pythagorean identities. So we have here a right triangle, and we have an angle of theta um, in this part. Now, the side that is adjacent to this angle other than the hypotenuse is labeled as A. So this is ADG, the adjacent side. And the side that is opposite to our angle, we call this as the opposite side, labeled as B. And then the longest side of our right triangle is our C, which is the hypotenuse. Now, by Pythagorean equation, uh, we relate these three sides into the form c squared is equal to a squared plus b squared. Now, if we multiply both sides of this equation by 1 over c squared, the result is 1 is equal to a squared over c squared plus b squared over c squared. Now we're going to extract the exponent, and then if we're going to use the trigonometric identities, so sine theta is equal to the opposite, that is b over c, and then the cosine of theta, that is the adjacent over the hypotenuse, so we have here a over c. Now we are going to substitute this one right here. So we have 1 is equal to the ratio of a over c is cosine of theta. So we have here cosine of theta. Sorry, it is now on the second term. But anyways, since addition is commutative, so this one is okay. Now b over c is sine of theta. So we have here 1 is equal to sine theta squared plus cosine theta squared. Or these two terms can be interchanged. It's because of the commutative property of addition. Now, uh, going back to our Pythagorean equation, if we're going to multiply this time by 1 over a squared, we will have this equation c over a squared is equal to 1 plus b over a squared. Now, we all know that c over a, so c is the hypotenuse over the over the adjacent, that will give us secant of theta, and then the ratio of b over a, that is the opposite of the adjacent, gives us the tangent of theta. Now we are going to substitute this right here in our equation, and it will become secant theta squared is equal to 1 plus tangent theta squared. This is our second Pythagorean identity, that is in terms of the tangent and the secant. And lastly, going back to our Pythagorean equation, if we're going to multiply the PE by 1 over b squared, the equation becomes c over b square is equal to a over b square plus 1. And if we're going to use these two trigonometric identities, we all know that the ratio of c over b, if we're going to refer our right triangle, c over b is hypotenuse over the opposite. That will give us the cosecant of theta. And the ratio of a over b, that is the adjacent over the hypotenuse, gives us the cotangent of theta. Now, if we're going to substitute this to our equation right here, we will arrive the third Pythagorean identity in terms of the cosecant of theta and the cotangent of theta, as shown right here. So these three are the Pythagorean identities in trigonometry. So try to um, comprehend this one, because these are very useful when simplifying trigonometric expressions. Now, let's proceed to the sum and difference identities for two angles. Now, let's say we have two right triangles. The second right triangle is placed on top of the first right triangle. So we're going to label these two right triangles. The first right triangle in the bottom, we have the right triangle ABC, and then the second right triangle is labeled as ACD. Now, we will put some angle for the first right triangle, that we have an angle alpha, and then the second right triangle we have angle beta. And now we're going to project a vertical line from D towards the side AB. So this vertical line is perpendicular to side AB. And now we're going to project also a horizontal line from our vertex C. And then this one right here is a right triangle, is a right angle. So if we're going to use our geometry, if this is alpha, this is also alpha. And since this is 90 degrees, so this one right here is uh, 90 minus alpha. So this interior angle right here is indeed equal to alpha. Now we're going to label uh, some additional uh, parts. So we have here the F and E. Now, we will start our first derivation in the right triangle ADE. So in the right triangle ADE, so this one right here, the sine of the angle for this right triangle ADE is the sum of alpha and beta. So we have ED, the opposite, this one right here, over AD, the hypotenuse. So the hypotenuse is this one. Okay. Now, from our figure, the side ED is can be expressed as the sum of EF, so this one, and DF, so this one right here. Okay, all over AD. Now, EF is also equal to this one, the side BC. So we have here BC plus DF over AD. Next, we are going to split the fraction into two parts. We have BC over AD plus DF over AD. Now, in the right triangle ABC, so this one right here, ABC, we have a relation for BC. So BC can be expressed as AC, so the hypotenuse, multiplied by the sine of alpha, okay, using the trigonometric identity sign. Now, additionally, in right triangle CDF, so CDF, this one right here, the our small right triangle. So we have an expression for DF, this side right here. So DF can be expressed as CD, which is the hypotenuse of this small right triangle, multiplied by the cosine of alpha right here. Now, we are going to substitute these two expressions to this equation, and it will become sine alpha plus beta is equal to our BC is AC sine theta over AD, then our DF is CD, so we have here CD cosine alpha over AD. Now, in the right triangle ACD, so ACD, the second right triangle that is mounted on the first right triangle, we have expression for cosine of beta. So cosine of beta right here is the ratio of this side, the adjacent side of this angle, that's AC, over the hypotenuse AD, this one. So we have here AC over AD. And then in the right triangle ACD, so ACD, so we have sine beta. So the sine of this angle beta is simply equal to the opposite side, that is CD, over the hypotenuse AD. So we have here sine beta equals CD over AD. So we have here AC over AD. This is equal to cosine beta. So we have here cosine beta, then sine alpha plus CD over AD, as we all know from the right triangle ACD, that is equal to sine beta. So we have here sine beta cosine alpha. And rearranging the terms, we have here the sine of the sum of the two angles alpha and beta simply equal to sine alpha multiplied by cosine beta plus cosine alpha sine of beta. Next, for the difference identity. So if we're going to get an expression for the difference of two angles, we're going to let beta is equal to the negative of beta. And we will use the previous expression that we have, or the previous equation for sine alpha plus beta that we have just derived. So this is now our equation. Sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. If we're going to substitute the negative of the angle of beta, so as shown right here, and if we use the previous identities that we have learned, which are the odd and even, we all know that the sine of negative angle is the negative of sine of the angle, and for the cosine of the negative of the angle is equal to the cosine of the positive angle. Substituting these two identities, it will give us sine alpha minus beta is equal to sine alpha cosine beta. So the cosine of negative beta right here is positive. And for the second term, sine of negative beta is negative. That is why the final equation for the difference of two angles for sine will give us sine alpha cosine beta minus cosine alpha sine of beta. Now let's proceed to the cosine. So in right triangle ADE, so ADE, so this right triangle right here, okay, we have the cosine of alpha plus beta. So we take the sum of this alpha and beta because this is the angle for this right triangle ADE. Okay, that is equal to the ratio of AE, this side right here, over the hypotenuse, which is AD. Now, AE can be expressed as the difference of AB and this small length that is equal to BE over AD. Then cosine alpha plus beta, so AB minus, take note BE is also equal to CF right here, okay, because they are um, parallel to each other, and the angle right here are all the interior angles for this rectangle are all 90 degrees. So we have BE is equal to CF. Next, we're going to split this fraction into two parts. These are AB over AD minus CF over AD. Now, in the right triangle ABC, so this one right here, ABC, AB can be expressed as AC cosine alpha. So AB is AC, the hypotenuse, multiplied by the cosine of this angle alpha. And then in the smaller right triangle CDF, so this one right here, CDF, we have an expression for CF. Okay, so CF is equal to the hypotenuse CD multiplied by the sine of alpha. So we all know CF is opposite to alpha. That is why we use the sign identity. Now, we are going to substitute these two expressions to our equation right here. So it will become, for AB, we have AC cosine alpha, and then over AD, minus for CF, we have CD sine alpha, and then over AD. Now, in the right triangle ACD, so we have here ACD, the ratio of AC, this one right here, AC over the hypotenuse AD, is simply equal to the cosine of beta. Okay? And then in the right triangle ACD, so this one right here, ACD, okay, the same right triangle, the ratio of CD is the opposite side of angle beta all over the hypotenuse, is simply equal to the sine of beta. So substituting these two expressions right here in our equation, we'll have the cosine of the sum of two angles is equal to the cosine of beta, cosine alpha, minus sine beta, then sine alpha. Rearranging, so we have the final equation for the cosine of the sum of two angles. So we have cos alpha cosine beta minus sine alpha sine of beta. And for the difference, we'll simply let beta equal to the negative of the angle beta. So if we're going to substitute this expression to our equation for cosine alpha plus beta, and then if we're going to use the odd and even identities for both sine and cosine, so we will end up with this equation. So cosine alpha minus beta is that's cosine alpha cosine beta minus sine alpha times negative sine of beta, and the final form should not be equal to this one. Sorry, I'll just edit this. Okay, let's continue. I already edited this part. So cosine alpha minus beta is equal to cosine alpha cosine beta, and this one right here, it will become positive due to the fact that from the add identity for sine, we have negative sine of beta is simply equal to the negative of sine. It's because sine is an odd identity. So the final equation for cosine alpha minus beta is this one. Now we will proceed to the tangent identity. So for the tangent, if we have tangent alpha plus beta, that is also equal to the ratio of the sine alpha plus beta all over the cosine alpha plus beta. We already know that one because the tangent of an angle is simply equal to the sine of the angle over the cosine of the angle. So we already derived an expression for sine alpha plus beta that is equal to this one, as well as for the cosine alpha plus beta, which is equal to this one. Now, the next step is to multiply this expression by a unit fraction equal to this one. So we're going to multiply 1 over cosine alpha cosine beta all over 1 minus cosine alpha cosine beta. I select this unit fraction with these corresponding expressions in order to eliminate some of the uh, the terms that are present in this expression, as well as transforming the other um, the other expression into a tangent um, a- tangent identity or tangent expression. Okay, so if we're going to distribute this one to each of the terms for both in the numerator and in the denominator, you will end up with this expression. So for the first term in the numerator, we have here sine alpha cosine beta all over cosine alpha cosine beta. And same goes with the second term in the numerator as well as the terms in the denominator. As you can see by inspection in the numerator, especially for the first term, we have a common factor right here, which is cosine beta. So this will be cancelled out. And we all know that sine alpha over cosine alpha gives us the tangent of alpha. And in the second term, both cosine alpha in the numerator and in the denominator are equal. So this will be cancelled out. And then sine beta over cosine beta gives us the tangent of beta. And in the denominator for the first term, cosine alpha and cosine beta are common for both in the numerator and in the denominator. So this fraction will be equal to 1. And then for the second term in the denominator, we have here sine alpha over cosine alpha. This will give us tangent of alpha. And for the second factor, we have sine beta over cosine beta. This will give us tangent of beta. Therefore, the result is equal to sine alpha over cosine alpha. So I already explained this one. So we will proceed to the next. So sine alpha over cosine alpha gives us tangent alpha plus tangent beta minus 1 minus tangent alpha. And this one right here is equal to the tangent of beta. So this is our sum identity for tangent. And for the difference identity for tangent, we'll simply let beta is equal to the negative beta and use the uh, add an even identity for tangent. So we all know that the tangent function is an add function. So we will use or we will substitute a negative tangent of beta. So it will become tangent alpha minus beta. So we have tangent alpha, and then for plus tangent of beta, so if we have plus tangent of the negative of beta, it will become negative tangent of beta right here. And in the denominator, we have 1. So instead of the minus, uh, it becomes plus due to the fact that the tangent of negative beta right here, if we're going to substitute that one, will become negative of tangent beta. So we have a negative multiplied by a negative that will give us a positive in our denominator side. So this is the difference identity for the tangent. Now to summarize, for the sum and difference identities, so for sine, you can use the mnemonics for sine alpha plus minus beta. So we have here sin cos cosine, no? Sine alpha cosine beta. And if we have plus or minus, so same goes. We have here plus minus. Then cosine alpha sine beta. So for sine, you will have sin cos cos sin. And the arrangement for the angles starts with the first angle alpha, then beta, and then for the second term, that is also the same. It is alpha and beta. And for the cosine, so cosine alpha plus minus beta, that's cos cos sin sin. That is the mnemonics. So cos cos sin sin, and then the arrangement of the angles are the same as the sine. However, the only difference for cosine is that if we have the sum of two angles, the sine that exists between these two terms is the opposite. So if that is plus, you'll take the minus, and if you have alpha minus beta, you will take the plus sign that separates these two terms. Okay, so for cosine, you have cos cos sin sin, and then the the signs are opposite to each other. So if you have plus here, you have minus right here, and if you have minus right here, you have plus right here. And then for the tangent, so you have your tangent alpha plus or minus beta. So you will have tangent alpha. In the numerator, you have plus and minus. But in the denominator, you have here minus plus. Because for sum of two angles in tangent, the denominator is negative. However, if we have the difference of the angle, only the numerator becomes negative, but the in the denominator, the sign that exists between these two terms is now positive. So try to comprehend these three sum and difference identities for sine, cosine, and tangent, because these are very useful. Now we will proceed to the double angle identities. The derivation for these identities comes from the sum identities, the sum and difference identities. So let's start with the sine. So for this derivation, we will let the alpha equal to beta, which is equal to um, an angle of theta. So for our derivation, or for the final equation, that is in terms now of theta, not alpha nor beta. Okay, this is our equation for the sum identities for sine. If we're going to equate these two angles into theta, so we have here sine theta plus theta, we have sine theta cosine theta plus cosine theta sine theta. As you can see, so sine theta plus theta becomes sine 2 theta. So this is why this identity is called double angle, because we have twice of the given angle theta. So since these two terms are equal, so we can combine this into 2 sine theta cosine theta. And this is our first double angle identity for sine. Next, we will proceed to the sum identities for cosine. Wherein the same with the sine, we will let alpha and beta to be equal to each other, and we will assign an angle for this, and that is equal to theta. So from the equation for cosine of alpha plus beta, so we have here cosine alpha cosine beta minus sine alpha sine beta. So substituting alpha and beta equal to theta, so we have cosine theta plus theta is equal to this expression right here. And as you can see, we have cosine theta, so it will become cosine theta squared. And same goes with the second term, it will become sine theta squared. Now, we can use Pythagorean identities for this one. We'll know that the cosine theta squared can be expressed as 1 minus sine theta squared. Or the sine theta squared can be also expressed as 1 minus cosine theta squared. Now, we will try to substitute first the sine of theta squared right here in our equation. So it will become cosine to theta is equal to cosine theta squared minus 1 minus cosine theta squared. Combining all like terms, you will end up with 2 cosine theta squared minus 1. So this is the double angle identity for cosine. But it has another form aside from this one. It's because we can still use this Pythagorean identity in our equation right here. So we're going to substitute this expression to our equation right here, and it will become 1 minus sine theta squared minus sine theta squared. So combining like terms, we will have 1 minus 2 sine theta squared. So this is the other form of the double angle for cosine identity or cosine function. Now, from some identities for tangent, so we're going to let alpha equals beta, which is equal to theta. So this is our tangent identity for sum of two angles. If then we're going to substitute uh, alpha equals beta, which is equal to theta, so we'll end up with this equation. So in the numerator, since we have tangent theta plus tangent theta, it will become 2 tangent of theta. Whereas in the denominator, we have here 1 minus tangent theta, so it will become 1 minus tangent theta squared. So this is the double angle for the tangent function. Now let's proceed to the half angle identities. For the half angle, we will refer our derivation from the result of the double angle identities. But this time, we will assign another angle, that is angle phi, and we're going to let that one equal to twice of theta. So this one is from the double angle. Therefore, the angle theta is simply equal to half of the angle phi. That is why it is called the half angle identity. Now we're going to substitute this expression for the angle phi, starting with the cosine. So cosine to theta equals 2 cosine theta squared minus 1. So 2 theta is equal to phi, and then theta is phi over 2. Next, our goal is to solve for cosine phi over 2. So we're going to um, transpose 1 to the left side. So it will become 2 cosine phi over 2 squared is equals to 1 plus cosine of phi. Then dividing both sides by 2. So you will have here cosine phi over 2 squared is equals to 1 plus cosine phi all over 2. And if we take the square root of both sides, you will have cosine of the half angle is equal to the square root of 1 plus cosine of the angle all over 2. So this is our first half angle identity. That is for cosine. Now, let's proceed to the sine. Okay, so we will use the cosine to theta. But this time, we will use the second form, which is 1 minus 2 sine theta squared. Next, substitute the expression for theta. So theta is equal to half of phi, and 2 theta is equal to phi. So we have here cosine phi is equal to 1 minus 2 sine phi over 2 squared. Now, solving for sine phi over 2. So we have here, you can transpose the 2 sine phi over 2 squared to the left side, and then cosine phi to the right side. So you will end up with this expression on the right side. And then if we divide both sides by 2, you will end up with this expression. So 1 minus cosine phi over 2. And then take the square root on both sides of the equation. You will have the sine of the half angle phi is equal to the square root of 1 minus cosine phi all over 2. So this is our second half angle. For the tangent, you'll simply take the ratio of the sine of the half angle and the cosine of the half angle, and then substitute. So for the sine of the half angle, substitute this expression right here. So we have here 1 minus cosine phi over 2. And then for the cosine of the half angle, substitute this expression. It will become 1 plus cosine phi all over 2. Now, since the 2 is common for both in the numerator and in the denominator, so that will be cancelled out, leaving the square root of 1 minus cosine phi all over 1 plus cosine phi. So this is the first form of the tangent of the half angle. But we can still modify this one. Okay, the other forms. So if we have tangent of the half angle is equal to this expression, if we're going to multiply a unit fraction, that is the square root of 1 plus cosine phi over 1 plus cosine phi, or in other words, the conjugate of the expression in the numerator, you will end up with this expression. So in the numerator, if you multiply 1 minus cosine phi times 1 plus cosine phi, you can use the sum and difference of two terms from algebra. So you will end up with 1 minus cosine phi square. And in the denominator, we have 1 plus cosine phi square, a binomial expression. Now, in the numerator, this one right here, from the Pythagorean identity, this is equal to sine phi square. Okay, and then sine phi square, since we have a square root, so the sine phi will be extracted from this radical expression. So you have sine phi, and same goes with the denominator, since the denominator is 1 plus cosine phi square, so a perfect square, so the square root of this expression is 1 plus cosine of phi. So this is the other form of the half angle for the tangent. Or instead of multiplying the conjugate of the numerator, we can also multiply another conjugate that is in terms of the denominator. So we're going to use this unit fraction, so square root of 1 minus cosine phi all over 1 minus cosine phi, multiplying this to our expression. So in the numerator, this is a binomial expression of 1 minus cosine phi squared. And then in the denominator, so use the sum and difference of two terms. So you have 1 minus cosine phi squared. And we can use the Pythagorean identity in our denominator. It will become sine phi square. So the exponent inside the radicand is the same with the index, so that will be cancelled out, meaning the expression will be extracted out from the radicand. So it will become tangent of the half angle is equal to 1 minus cosine phi all over sine phi. So these are the forms of our tangent of the half angle. Now we'll proceed to the product to sum identities. So the product to sum identities can be derived from the sum and difference identities, starting with sine. So we have sine alpha plus beta is equal to this expression, and we also have sine alpha minus beta is equal to this expression. Now, if we're going to add these two, it will become sine alpha plus beta plus sine alpha minus beta. And on the right side of these two equations, notice that cosine alpha sine beta will be cancelled out because they have opposite signs, leaving sine alpha cosine beta. So we have 2 times sine alpha cosine beta. Next, we're going to multiply both sides by 1/2 so that the result will be sine alpha cosine beta is equal to 1/2 of this expression right here. So we have sine alpha plus beta plus sine alpha minus beta. So this is our first product to sum identity. It is called product to sum identity. It's because on the left side we have the product of the sine and the cosine of the angles alpha and beta, and it is transformed into the sum of the identities. So we have sine alpha plus beta plus sine alpha minus beta. Next, we're going to subtract the two identities. So the first one is adding the two identities. So this time we are going to subtract these two identities. So we have sine alpha plus beta equal to this expression minus sine alpha minus beta, which is equal to the expression. We're going to subtract these two. We have sine alpha plus beta minus sine alpha minus beta. And for the first term, so since they are alike and since the operation is subtraction, so they will become 0. And for the second term, we have cosine alpha sine beta. Since they're opposite sign, so they will be added. As a result, we have here 2 cosine alpha sine of beta. Then multiply both sides by 1/2 or divide both sides by 2. You will end up with this equation. We have cosine alpha sine beta is equal to 1/2 sine alpha plus beta minus sine alpha minus beta. So this is our second product. So product of cosine alpha and sine beta to sum. Okay. Next, uh, by the way, maybe some of you may get confused with the word sum because we have here minus. Now this one can also be written as plus the negative of sine alpha minus beta. Okay, let's proceed to the sum and difference identities for cosine. So for cosine, we have these two equations. If we're going to add these two, it will become cosine alpha plus beta plus cosine alpha minus beta. And as you can see in the first term, so both of these terms are alike. And since the operation is addition, so we have here 2 cosine alpha cosine beta. But on the second term, since they are opposite to each other, they have opposite sign. So both of them will be cancelled out and will become 0. Next, multiply both sides by 1/2. We will now have our third product to sum identities, that is cosine alpha cosine beta is equal to this expression. Now, how about if we're going to subtract the sum and difference of cosine? So it will become cosine alpha plus beta minus cosine alpha minus beta. Now on the right side of our equation, of our two equations, since the first term are they have the same sign, so both will become 0 if you're going to subtract both. And then for the second term, since they are opposite in sign, okay, so we have here uh, 2 sine alpha sine beta, but I guess it will become negative. So therefore, instead of alpha plus beta, I guess the first term that comes on the left side of the equation should be alpha minus beta because we still have negative right there. Sorry, I will going to edit this one. Please wait for a moment. Okay, I already edited this part. So let's go back in this section. So since we have negative sine alpha sine beta minus positive sine alpha sine beta, so the result will be negative 2 times sine alpha sine of beta. So the next step is we're going to multiply both sides by, instead of positive 1/2, we have here negative. So this should be negative 1/2. So it will become sine alpha sine beta is equal to 1/2. So instead of cosine alpha plus beta to be at the first, to become in the first term, so we interchange these two. So the first one that comes uh, before the minus sign is the cosine alpha minus beta. So we have cosine alpha minus beta minus cosine alpha plus beta. So this is our last product to sum identities. Now let's proceed to the sum to product identities. So the sum to product identities are derived using the result from the product to sum identities. Now from the product to sum identities, we are going to let some, or let another angle that will represent alpha plus beta and alpha minus beta, because from the product to sum we see lots of expression that involves alpha plus beta and alpha minus beta. So for alpha plus beta we will assign an angle theta for this one, and then for alpha minus beta we will assign the angle phi. Now if we're going to add these two, we have a new expression that is alpha plus I mean sorry theta plus phi is equal to twice alpha, because beta in the second term will be cancelled out. So therefore alpha is equal to theta plus phi all over 2. Now if we subtract these two, we'll end up with theta minus phi is equal to, so alpha right here will be cancelled out, it will become 0. Then we have beta minus the negative of beta, so we have positive 2 beta. So beta is equal to theta minus phi all over 2. Now we are going to substitute these new expressions to our product to sum identities in order to generate the sum to product identities. Now let's start with the product to sum identities for sine and cosine. So we have sine alpha cosine beta is equal to 1/2 multiplied by sine alpha plus beta plus sine alpha minus beta. Rearranging this or multiplying both sides of the equation by 2, so you will have sine alpha plus beta plus sine alpha minus beta is equal to 2 times sine alpha cosine beta. This is called sum to product identity. It's because on the left side we have sum of the sine of the angles alpha plus beta equal to the product of the sine and cosine on the right side of the equation. Next, substituting the expressions for alpha and beta in terms of theta and phi. So for the left side of the equation, alpha plus beta will become theta. So we have here sine theta. And then alpha minus beta will become phi. So we have here plus sine of phi is equal to 2 times sine alpha. So alpha right here is theta plus phi. So we have here theta plus phi all over 2. Then cosine theta minus phi all over 2. So this is our first sum to product identity. Next, we'll proceed to the product to sum identities for cosine and sine. So we have cosine alpha sine beta is equal to this expression. Now substituting the expressions for alpha and beta. So we will have here, by the way, before that, so in getting this equation, you are going to multiply 2 on this equation. So you will arrive this equation, and then that is the time that you are going to substitute the expressions for alpha and beta. So sorry, I'll jump the the, the step, okay? Or sorry if I skip that process. Okay, let's continue. So sine alpha plus beta minus sine alpha minus beta is equal to 2 cosine alpha sine of beta. So alpha plus beta from this equation that is equal to theta. So we have your sine theta minus alpha minus beta, which is this one, is equal to phi. So that we have sine phi is equal to 2 cosine. So for alpha, that's theta plus phi over 2. And then for beta, that is theta minus phi all over 2. As you can see from this section. Okay, now this is our second sum to product identity. For the last one, we will refer to our cosine and sine product to sum identity. So this is our cosine and cosine. So we have cosine alpha cosine beta is equals to 1/2 of this expression. Next, multiplying both sides by 2, you'll end up with this equation. And then substituting the expressions for alpha and beta, you will arrive with our third sum to product identity, which is equal to this one. Okay, we still have the last one. It is this is the last. Okay, so we have the product to sum identity for sine and sine. So we have sine alpha sine beta is equal to this one. So multiplying both sides by 2, you will end up with this equation. Then substituting the expressions for alpha and beta, you will arrive with this equation, okay, which is the sum to product identity for cosine and cosine. So we have cosine alpha, cosine phi, sorry. This is cosine phi minus cosine theta is equal to 2 sine theta plus phi all over 2 times the sine of theta minus phi all over 2. As you can observe for our last sum to product identity, the only difference for this identity from the three sum to product identities that we have just derived is that phi comes first before theta, because for the previous three sum to product identities, it theta will come first before phi. It's because of the minus sign right here. Okay, now let's have some sample problems in order for us to apply those identities when simplifying trigonometric expressions or solving trigonometric functions or some equations. Okay, now let's have our first example, that is using identities. We are going to simplify sine x plus cotangent of x times the cosecant of x. So how are we going to simplify this one? So first, uh, your first um, or the first thing that you should remember is that you are going to rewrite the given expression using the sines and cosines, because these two trigonometric functions are the commonly used functions and it is easier to manipulate. So if you can observe from the given trigonometric expression, it contains cotangent of x. So we are going to transform that one. So from sine x plus cotangent of x cosine of x, as you can see, uh, the equivalent expression for cotangent of x in terms of sine and cosine are cosine x sine of x. Note that cotangent of x is the reciprocal of the tangent of x. So instead of sine and cosine, you have cosine over sine x right here. Next, multiply cosine of x with cosine of x so that you will generate the final expression in the numerator. So we now have sine x plus cosine x squared all over sine x. Next is we're going to combine the two terms, that is sine x and this fraction. So the LCD is sine x, so we have sine x, and then in the first term in our numerator we have here sine x squared, due to the fact that if you're going to divide sine x, or if you're going to divide our final expression or our LCD sine x divided by 1 then multiplied by sine x, you will end up with sine x squared. Now on the second term, we have cosine x squared. As you can observe in our numerator, we can use Pythagorean identity. Remember that the sum of sine x squared and cosine x squared will give us 1. Therefore, we have there 1 over sine x, and 1 over sine x, as we all know, this is the reciprocal of the cosecant of x. So the A simplified form of this given expression is equal to the cosecant of x. And this is our final answer. Now let's proceed to our second example. For this example, we are going to use the add and even identities. So simplify 1 over 1 plus cosine of negative x plus 1 over cosine of x. We will use the even identity for cosine so that we can simplify the negative angle that is present in the denominator of the first term. So for the even identity for cosine, we all know that the cosine of negative angle is still equal to the cosine of the positive angle x. So substituting that one, so the first term will become 1 over 1 plus cosine of x instead of the negative angle. Then plus copy the second term. So that's 1 minus cosine of x. Next is we're going to combine these two fractions. The LCD for this are the product of the denominators. And these are 1 plus cosine x and 1 minus cosine x. So you will end up with this expression. So in the first term in our numerator, so this LCD divided by this expression, the result is 1 minus cosine x. And same goes with our second term. If we divide our LCD with 1 minus cosine x, that will give us 1 plus cosine x and multiplied by 1. So you will have here 1 plus cosine x. Next is simplify the numerator and the denominator. So for the numerator, we have 1 plus 1, that is 2. And then we have negative cosine x and positive cosine x. So same term with opposite signs. So that will equal to 0. And for the denominator, we can use the sum and difference of two terms. So you have, if you have u plus v and u minus v, so the result is equal to u squared minus v squared. So we're going to use this. And it will become 2, the numerator all over. So 1 squared minus cosine x squared. And as you can observe in the denominator, we can use the Pythagorean identity for sine and cosine. So modifying the first Pythagorean identity for sine and cosine, you will arrive sine x squared is simply equal to 1 minus cosine x squared. So substituting this one right here, so you will have 2 over sine x squared. And we all know that the reciprocal of sine x is equal to the cosecant of x. So if we have 1 over sine x, that will give us cosecant of x. And since sine x here is squared, so cosecant of x is also squared. So the final answer is 2 cosecant of x squared, due to the fact that, again, the reciprocal of cosecant of x is sine x and vice versa. Now let's proceed to example number 3, wherein this is all about the cosine of a sum. Now our goal here is to find the exact value of the cosine of 75 degrees without using a calculator. So we can get its exact value even if we don't have a calculator by simply using the identities that we have just derived and have just discussed. So first, we are going to use the sum of two angles for cosine. It's because the 75 degrees can be broken down into 45 degrees plus 30 degrees. So from the sum of two angles for cosine, we have cosine alpha plus beta is equals to cos sin sin. And since this is sum of two angles, so the middle or the sign that separates these two terms is minus, which is the opposite. Okay, try to remember the mnemonics that I have discussed to you. Okay, so alpha is the first angle, that's 45 degrees, and then beta is the second angle right here, 30 degrees. So we have cosine 45 degrees plus 30 degrees is equal to cosine 45 cosine 30 minus sine 45 sine 30 degrees. And we all know that these two angles right here, the 45 degrees and the 30 degrees, are both special angles, and we already discussed the value of their cosines and sines and even the tangents. So use the value of cosine and sine for special angles. So for cosine 45, that is also equal to the sine of 45, and that is equal to square root of 2 over 2. For cosine of 30, that's square root of 3 all over 2. And then for sine 30, that's 1/2. So substituting these values to our equation, so we have for cosine 45, we have square root of 2 over 2. For cosine 30, that will give us square root of 3 over 2. Then minus for sine 45, that is square root of 2 over 2. Then for sine 30, that is 1 half. So simplifying this one, for the first term, square root of 2 times square root of 3, that will give us square root of 6. This is valid because they have the same index, remember? So in the denominator, we have here uh, 2 times 2. So this must be 4, but right here this is 2. So I guess I'm going to uh, edit this one first. Okay, so I already edited this part. So 2 times 2 is equal to 4. And then for the second term, we have square root of 2 times 1. That will give us square root of 2. And then in the denominator, that is 4 because 2 times 2 is 4. Next, combine these two fractions. So it is easier to combine since these fractions are similar fractions because they have the same denominator. So the final answer is square root of 6 minus square root of 2 all over 4. So this is the value of our cosine, the exact value of our cosine 75 degrees without using a calculator. Next, example number 4. For this example, we are going to use the add and even and the cofunction identities respectively. So the problem statement is show that cosine of theta minus pi over 2, so pi over 2 is 90 degrees, is equal to sine theta is an identity. Okay, we are going to manipulate the left side of the equation by factoring -1 inside the parentheses. So this one right here. We do this so that we can get the cofunction of the angle theta. So the cosine of theta minus pi over 2 can also be rewritten as cosine of the negative. So we extract the negative or we factor the negative. So negative, what's left is positive pi over 2 and the negative of the theta. And now we're going to use the even identity for cosine. So if we have a cosine of negative theta, we have a cosine of theta. So for from this expression, we will let that, or we can use another angle for this one. No? So if we have a cosine of negative x, it is also equal to the cosine of x, wherein our x here is equal to the expression inside the parenthesis, which is pi over 2 minus theta. So this one is simply equal to cosine of x, which is equal to the cosine of pi over 2 minus pi, as you can see. Then use the cofunction identity for cosine. So we all know that the cosine of the complementary angle for theta is equal to the sine of theta. So that is equal to sine of theta, and therefore this is equal to the right side of the equation. So both these two expressions are indeed an identity. Next, for example number 5, we are going to use double angle identities in order to find the exact value for starting with sine 120 degrees, then cosine 120 degrees, and lastly, the tangent of 120 degrees. So we can get the exact values for these three even if we're not going to use the calculator. But or in order to do that, we will use the double angle identities, and we're going to express the given angle as a double angle. So we all know that 120 degrees can be expressed as twice of 60 degrees. And we're going to let theta equal to 60 degrees so that we have 2 theta. And that is for the double angle. Next, we are going to use the double angle identity starting with sine because we want to know the value for sine 120. So we have sine 2 theta is equal to 2 sine theta cosine theta. So sine of 2 times 60, that's sine 120, is equal to 2 sine 60 cosine 60. So 60 degrees is a special angle. So we all know that sine 60 is square root of 3 over 2, and then cosine 60 is 1 half. So multiplying this one, 2 will be cancelled out. So we have square root of 3 all over 2. So therefore, the sine of 120 degrees is equal to square root of 3 all over 2. Next, we'll proceed to the cosine. What will be the value of cosine 120? So we will use the double angle identity for cosine. So you have two different forms for the cosine. So you may select either of those two. Now, in my case, I use cosine 2 theta equals 2 cosine theta squared minus 1. We have cosine 120 is equal to 2 cosine 60 squared minus 1. So cosine of 60, as we all know, this is 1 half. So we have here 2 times 1 half squared minus 1. Simplifying further, so 1 half squared is equal to 1/4. Then this will be cancelled out, leaving 2 in the denominator. So you have 1 half minus 1, and that is equal to negative 1 half. Therefore, the exact value for cosine 120 degrees is equal to negative 1 half. And lastly, for the tangent, so we're going to use the double angle identity for tangent. That's tangent 2 theta is equal to this expression. So next is substituting the values. So theta is 60 degrees. So we have here tangent 120 is equal to 2 times the tangent of 60 over 1 minus the tangent of 60 degrees squared. Now the tangent of 60 is equal to square root of 3. Now it's okay, class, if you already know the cosine and sine of the special angle 60, because even if you don't know the tangent of 60, you can use the identity for tangent, that is the ratio of the sine over the cosine. So sine of 60 is square root of 3 over 2 divided by the cosine 60, that is 1 half. You'll end up with square root of 3. Now simplifying this expression, you have 2 square root of 3, and then in the denominator, square root of 3 squared, that will give us 1 minus 3, and that will give us 2 square root of 3 all over negative 2, and it will become negative square root of 3. So this is the value of our tangent 120 degrees, the exact value of tangent 120 degrees without using calculator, by simply using the double angle identity and some modification of its angle. Now let's proceed to example number 6. In this example, we will use the half angle identity. So find the exact value of tangent negative 15 degrees using half angle identity. Now we will let phi equal to negative 30 degrees, so that if we divide the negative 30 degrees by 2, we'll end up with negative 15 degrees. So therefore, the given angle, which is negative 15 degrees, can also be expressed as half of negative 30 degrees. And since we express the angle as a half, so we will use the half angle identity. And since the given is tangent, so we will use the half angle identity for tangent. That is, it has three forms, so you can use either of those three forms. Now, in my case, I will use this form, wherein the tangent of the half angle is equal to the sine of phi over 1 plus cosine of phi. Now, substituting the values, so phi over 2, that's negative 30 degrees over 2, is equal to sine of negative 30 degrees over 1 plus cosine of negative 30 degrees. Now use the value of cosine and sine for the special angle 30 degrees. So for cosine 30, that's square root of 3 over 2. Then for sine of 30 degrees, that's 1 half. Next, aside from these values, we're going to use the even and odd identities for both cosine and sine respectively, so that the tangent of, again, negative 30 over 2, that's negative 15 degrees, is equal to, so for sine negative 30 degrees, that is equal to the negative, okay, this is equal to the negative of sine of 30. And sine of 30 is 1 half, so we have here negative 1 half, because sine is an odd uh, function. Next, in the denominator, the cosine of the negative angle is positive, so cosine of the angle. So cosine of 30 will give us square root of 3 over 2. That's why we have a positive value in the denominator. Next, simplifying, especially in the denominator. So we have here 2 plus square root of 3 all over 2. So the LCD is 2. Next, take the reciprocal of the denominator. So you have negative 1 half times 2 over 2 plus square root of 3. And we have here negative 1 all over 2 plus square root of 3. Next is we're going to rationalize the denominator to simplify this one further. So the conjugate of 2 plus square root of 3 is 2 minus square root of 3. Simplifying this one, you will have negative 2 square root of 3. Then use the sum and difference of two terms in order to simplify the denominator. So you have 2 squared minus square root of 3 square. Next, uh, the denominator becomes 4 minus 3. So you'll end up with 1 in the denominator, or that is equal to negative times 2 minus square root of 3. And if you're going to distribute the negative sign, it will become square root of 3 minus 2. So this is the um, exact value of the tangent of negative 15 degrees. Next, we will use any identities to find the sine of the half angle. That's theta over 2. If the sine of the angle is equal to 3/5, and then the angle lies from 90 degrees to 180. So that's pi over 2 to pi. Okay, we will use the half angle identity for sine, since we're given with sine of the half angle. So sine of the half angle is simply equal to the square root of 1 minus cosine of theta all over 2. Now, in our problem statement, we're only given with sine theta that's equal to 3/5. But in the expression for the sine of the half angle, we have cosine of theta. So we will use the Pythagorean identity so that we can get a value for cosine of theta given the value of sine theta. So we have here 1 is equal to sine theta squared plus cosine theta squared. Our goal is to solve for the cosine theta. So we will transpose sine theta squared on the other side. So we have this equation. Next is we take the square root on both sides of the equation. So you end up with cosine theta is equal to square root of 1 minus sine theta squared. Next, substitute the value for sine theta, that's 3/5. So you have square root of 1 minus 3/5 square. Simplifying this, it will become square root of 1 minus 9 over 25. Then further simplification, that is combining these two terms, you'll end up with 25 minus 9 over 25. So you have square root of 16 over 25. Since both numbers are perfect square, so you'll end up with plus or minus 4/5. So we have two values for our cosine of theta. But we only pick one because we are given with an interval. So we all know that the angle of theta lies from 90 degrees to 180. So this is probably located in the second quadrant. And the value of the cosine there is always negative. So therefore, we will take the negative value of cosine of theta, and that is equal to negative 4/5. So we will ignore the positive because it doesn't make any sense since we're given with an interval of the theta. Okay? So just remember this one. The cosine in the second quadrant is negative. That is why we use the negative value. Okay, we will substitute this value to our first equation for the sine of the half angle. So we have here square root of 1 minus, so cosine of theta is negative 4/5 all over 2. So simplifying further, you have 1 plus 4/5 all over 2. So we have plus or minus 3 square root of 10 all over 10. Next, uh, going back to our interval. So if theta is between 90 and 180, then the half angle of, or half of theta, so meaning for the given interval, if we divide both sides, or if we divide all sides of the inequality by 2, so we end up with pi over 4 less than pi over 2, then less than pi over 2. So the new interval will now be from pi over 4, this is 45 degrees, up to pi over 2, and this is 90 degrees. So this angle surely lies in the first quadrant. So therefore, the value of sine in the first quadrant is always positive. That is why we will use the positive answer for sine of the half angle, and that is the positive 3 square root of 10 all over 10. So this is our final answer. Again, for this example, it's not about finding the values. uh, you also need to take into account the given interval. It's because that will give us a sign whether to select the negative answer or the positive answer, especially when dealing with square root of a certain value. Okay, since half angle has a radical expression, so we will expect, especially this is square root, you will expect two answers. And in order to select whether positive or negative answer, try to refer from the given interval, if there is a given interval. If there is no given interval, so therefore you're going to consider the two answers, both the positive and the negative. So the interval are our uh, limiting condition. Okay. Now let's proceed to example number 8, wherein this is all about expressing a product as a sum. So we will rewrite the expression sine 12 degrees multiplied by cosine 9 using product to sum identity. So from our product to sum identity for sine and cosine, so you will have this equation. Substituting the values, you have sine 12 cosine 9 is equal to 1 half sine 12 plus 9 plus sine 12 minus 9. So you will end up with 1 half sine 21 plus sine 3 degrees. And this is our exact answer in expressing product as a sum. Next, we will rewrite the sine 60 minus sine 40. So this is the difference into a product identity by using the difference to product identity for sine sine. Since the given is sine sine, so we will use the sine sine difference to product identity. So use this equation, substituting the values. So for theta, that is the first angle right here, that's 60. Then for phi, that is the second angle, that is 40. So you have 60 plus 40 all over 2, that's for the cosine. Whereas for the sine, you have here 60 minus 40 all over 2. Simplifying further, so 60 plus 40, that's 10t all over 2. Then 60 minus 4t, that's 2t all over 2. Simplifying further, so in the right side of the equation, you have 2 cosine 10t all over 2, that's 5t. And then 2t all over 2, that is t. So you have the final answer, 2 cosine 5t multiplied by sine t. So this is the other expression for sine 60 minus sine 40. Now, let's proceed to the discussion on verifying trigonometric identities. Now, in verifying trigonometric identities, there is no particular procedure that works for all identities. So we must manipulate one side of the equation until it looks like the other side. Or you can select, depending on the given trigonometric identities, you can manipulate either the left, leaving the right, or you can manipulate the right, leaving the left. So it depends. It's because there are some cases that the left side is more complex than the right side, or otherwise. Okay? So these are my suggestions when verifying or proving trigonometric identities. So the first one is start with the more complicated side of the equation. So transform it in a step-by-step process until it looks exactly like the other side. So if the left side is more complex than the right, so start with the left. Then use those trigonometric identities that we have just discussed in order to transform the complex trigonometric identity into a simple identity that is equal to the other side. That is how you prove. Now, in proving, um, do not transpose the left side to the right side, and do not multiply both sides by something. So you only need to modify uh, the one side. So not both of them on the same time and at the same value that you're going to multiply or add, because it will affect its value. Now the second one, as much as possible, combine all sums and differences of fractions into a single fraction. If there are fractions, you're going to combine. Next, do analysis and then find a way to apply the fundamental identities. So uh, starting with the add even identities, then to sum and difference, half angle, double angle, until the product of sum identities. But last two identities, the product to sum and the sum to product, those are rare identities that are not uh, totally used in verifying trigonometric identities. Okay, number 4, make use of the algebraic techniques to manipulate one side of the equation until the other side of the equation is achieved. So try to review your concepts in factoring and uh, uh, in canceling some common factors, and in uh, in creating a conjugate out of a given expression that contains some two terms that are separated by minus or plus, or if there is a radical expression, and then try to remember how to combine two dissimilar fractions, because those things are very useful in verifying trigonometric identities. Number five, try to rewrite the more complicated side in terms of sines and cosines. So this is the simplest way in verifying trigonometric identities. So even the complexity, try to remember that you can start by rewriting or by changing the complicated terms in terms of sines and cosines. So if there are some cosecant, secant, cotangent, and tangent, so try to transform them into sines and cosines to make the verification much simpler. Number six, if you are not getting anywhere, so do not be afraid to stop and start over again. Of course, this is very important. So uh, do not lose hope. So if you cannot verify the trigonometric identity for the left side, so try to uh, modify the right side. Okay, maybe the right side is more friendly compared to the left side, or easier to manipulate. Okay, so let's have our first example. This is all about changing to sines and cosines to verify an identity. So this is the first step. You must transform those reciprocals of our three basic identities: the sine, the sine, cosine, and tangent. So the reciprocals are the cosecant, secant, and the cotangent. You're going to change those in terms of sines and cosines. Even tangent, not we can rewrite tangent in terms of sines and cosines. Okay, for our first example, verify the identity sine theta tangent theta plus cosine theta is equal to secant of theta. Now, since the left side is more complex compared to the right side, so manipulate it first. So sine theta tangent theta plus cosine theta, we're going to transform this in terms of sine and cosine. So tangent can be expressed as sine theta over cosine theta. Now multiplying sine theta and sine theta, so you will have sine theta squared over cosine theta plus cosine theta. Next is combine the two terms. The LCD for the two terms is cosine theta. So in the first term in our numerator, that's sine theta squared. Then on the second term, you have cosine theta divided by 1. That's cosine theta multiplied by cosine theta. So you will end up with cosine theta square. And as you can see, the expression in the numerator is very familiar. So we can use the Pythagorean identity. So sine theta squared plus cosine theta squared is simply equal to 1. If we refer our analysis from the Pythagorean identity for both sine and cosine. So the numerator becomes 1, then all over the denominator, which is cosine theta. And since 1 over cosine theta is the uh, the equivalent of the secant theta, because both are reciprocal with each other. So 1 over cosine theta is simply equal to secant of theta. And we have just verified that the left side of the equation is equal to the right side of the equation. Next, for this example, we are going to use factoring to verify an identity. So verify the identity cosine theta minus cosine theta times sine theta squared is equal to cosine theta cube. So since the left side again is more complex, so manipulate it first. So factor cosine theta from the two terms. So as you can see, this is our first term, this is our second term. We have a common uh, expression for both terms, that is cosine theta. So we're going to factor out that one. So this left side becomes cosine theta times 1 minus sine theta squared. So we have just factor out the cosine theta. Next, the expression inside the denominator is very familiar. We can use the Pythagorean identity because 1 minus sine theta squared is simply equal to cosine theta squared. So then the resulting expression becomes cosine theta times cosine theta squared. And lastly, using the law of exponent, so we have cosine theta cubed. And as you can see, we have just proved that the left side of the equation matches the expression on the right side. And and it is verified. Next, uh, example number 3, using two methods to verify an identity means that we're going to manipulate both the sides of the equation, the left side and the right side. Now let's start with the first method, that is the manipulation of the left side, because if you can see, as you can see, both sides of the equations are somewhat complex. Okay, for the left side, we're going to split the fraction into two fractional terms. So the 1 plus sine x over cosine x becomes 1 over cosine x plus 1 over sine x plus sine x over cosine x. Now 1 over cosine x, this is equal to the secant x, and then sine x over cosine x is simply equal to the tangent of x. So as you can see, for method 1, the left side is indeed equal to the right side, okay, because they are the same. Now you can also manipulate the right side in order to come up an expression that is similar or equal to the left side. So for the right side, we can change the trigonometric functions that are present in terms of sines and cosines. So for secant x plus tan x, we'll know that secant x is the reciprocal of cosine, so you have 1 over cosine x. Then tangent is sine x over cosine x. Next is we're going to combine the two fractions. Since these fractions are similar to each other, so just copy the denominator, so cosine x, and then add their numerators. So 1 plus sine x. As you can see, the resulting expression is equal to the expression on the left side. So therefore, we have just proved these two identity. They are equal to each other. Okay. So in this example, you can manipulate either the left or the right side. Next, combining fractional expressions to verify an identity. So verify the identity, cosine x over 1 plus sine x plus 1 plus sine x over cosine x is equal to 2 secant x. In this example, it is very obvious that the left side of our equation is very complex, or more complex compared to the right side. That is why we will focus our uh, manipulation on the left side. So combine, the first step is to combine these two fractions with LCD equal to 1 plus sine x and cosine x. So this one divided by 1 plus sine x, the result is cosine x multiplied by the numerator, that will give us cosine x squared. The next, for the second term in the numerator, divide this one by cosine x, that will give us 1 plus sine x, and then 1 plus sine x multiplied by the numerator, that will give us 1 plus sine x squared. Next, expand this binomial expression in the numerator by using FOIL method. So you have cosine x squared plus, so square the first, that's 1, then multiply the two terms, that's 1 times sine x, that's sine x, then multiplied by the exponent, so we have here 2 sine x, and then square the last, so you have sine x square all over 1 plus sine x times cosine of x. Next is um, combine like terms in the numerator, so you have cosine squared x plus sine squared x plus 1 plus 2 sine x. I guess uh, there are no like terms, but what I did here is I uh, put the sine x squared closer to cosine x squared. It's because we have an identity that can be applied for these two, and that is the Pythagorean identity. We all know that cosine x squared plus sine x squared is equal to 1. So we have here 1 plus 1 plus 2 sine x. Next, simplifying the numerator further, that's 2 plus 2 sine x. And then factor and simplify. So in the numerator, the common is 2, so you have 2 times 1 plus sine x. And as you can see, the there's a common factor in both the numerator and in the denominator, and that is 1 plus sine x. So we can uh, cancel out these factors, leaving 2 over cosine x. And 2 over cosine x can be also written as 2 times 1 over cosine x, right? And we all know that 1 over cosine x is equal to secant x. So the final answer here is 2 secant x. As you can see, we have just verified that the left side expression is equal to the right side expression, which is 2 secant x. Okay, next, example number 5, multiplying an identity fraction to verify an identity. So the problem statement goes like this: verify the identity sine x over 1 plus cosine x is equals to 1 minus cosine x over sine x. Now both the sides of the equations are complex, so you can pick either of the two sides. So for me, I select the left side for analysis. So for the left side, I will going to multiply an identity fraction, or I will going to uh, multiply an identity fraction that contains the conjugate of the denominator. So the denominator is 1 plus cosine x, so I will going to multiply it with 1 minus cosine x over 1 minus cosine x. Then simplify. So if we're going to multiply the numerator, it will go like this. So sine x times 1 minus cosine x. Whereas in the denominator, since both are binomial and they only differ with the sign that separates the two terms, so we can use the sum and difference of two terms, that is u minus v multiplied by u plus v. So the result here is u squared, minus v squared. So I have here 1 minus cosine x square. Then we are going to apply Pythagorean identity in the denominator, because we all know that 1 minus cosine x squared is simply equal to sine x squared. So we have here sine x times 1 minus cosine x over sine x squared. As you can see, there's a common factor in the numerator and in the denominator, and that is sine x. So cancel out sine x, we only have 1 that is left in the denominator, that is for sine x. So we have here 1 minus cosine x over sine x, and we have just proved that the left side expression matches the right side expression. Next, verify an identity by modifying the two sides. So here we're given with an identity sine x plus 1 all over sine x is equal to the negative of cotangent x squared all over 1 minus cosecant x. So both are complex, and the right side also contains some trigonometric functions other than sine and cosine. So we are going to modify both sides so that we can verify if after the modification process, if we found out that if the expression that we are going to get for both sides are the same, so we can say that this is an identity, okay, or they are equal to each other. Now let's start with the left side. So for the left side, we have sine x plus 1 over sine x. We're going to split the fraction into two parts. So it will become sine x over sine x plus 1 over sine x. So simplifying further, sine x over sine x becomes 1. Then 1 over sine x is equals to cosecant of x, the reciprocal of sine x. Now, we are going to, or we will proceed to the next um, side, that is the right side, and let's try to modify that one so that we can arrive 1 plus cosine x. If we can arrive this one, then these two are identity. Now on the right side, we are going to apply Pythagorean identity in the numerator. That is for the cotangent and cosecant. So we all know that cosecant theta squared is equal to 1 plus cotangent theta squared. So applying this one, sorry, I forgot to edit this. So instead of theta, we will use x as our angle. Okay, let's continue. So I have just edited the uh, the assignment of the angle. So instead of theta, I put here x. So let's continue. In the right side, we have negative cotangent x squared over 1 minus cosecant x. So applying the Pythagorean identity for cotangent and cosecant. So the cotangent x squared is equal to cosecant x squared minus 1. And then next is we are going to distribute the negative right here to our numerator, and it will become 1 minus cosecant x squared all over 1 minus cosecant x. Next is we are going to factor the numerator completely, because this is of the form u squared minus v squared. So the factors are u plus v multiplied by u minus v, wherein our u is equal to 1, then v is equal to cosecant of x. So the factors are 1 minus cosecant x times 1 plus cosecant x. As you can see, there is a common factor that exists in the numerator and in the denominator. So we are going to uh, cancel out these two factors. And what's left is 1 plus cosecant x. As you can see, we have just verified that the expression on the left side that uh, we have solved from the first step is 1 plus cosecant x. That is similar to what we have arrived in the second part of our solution. That is for the right side. That is equal to 1 plus cosecant x. Therefore, these two are identity, or they are equal to each other. So thank you and God bless. I hope you learned something, and make sure to practice uh, simplifying trigonometric identities as well as proving trigonometric identities. So in order to remember those trigonometric identities, you may comprehend or memorize those formulas, but those are many. So I recommend you to derive those um, identities using my technique that I have just introduced to you in this video. Okay, so once again, thank you and God bless.